Okay, so now I'm going to derive Noether's inequality, or Noether's theorem. So this is Max Noether, this is not Emmy Noether. Okay, so this is going towards the Noether theorem. So we're going to use the proof technique from Caswell-Novo's inequality. Let me just state a fact. Okay, so let C be a smooth curve. Okay, so this is going to be over an algebraically closed of characteristic 0 for this talk. So D is going to be a divisor curve here. And suppose that the map induced by phi here to here, so the image is birational to, so let's say that this is birational. It is birational. So it's birational onto its image. So this is a morphism, but the problem is, and then they're both going to have the same function fields, but the issue is that here this could maybe be like singular. Okay, so it's going to be kind of weird. Okay, okay. So then, in this situation, the following are equivalent. Okay, so the following are equivalent. One, that C is extremal. It's extremal via phi of D, i.e. in the Caswell-Novo. So this is, I mean, extremal meaning that this is what it means. It means that we actually have equality in Caswell-Novo's theorem. Okay. The second thing is that this linear series, okay, is equal to the other linear series coming from hypersurface divisors. So for all L bigger than 1. Okay, so for L equals 1, it's clear by definition. And then here, yeah, so these were the degree L hypersurface divisors. Okay, 3. The third thing is that for all L greater than or equal to 0, this map O of D here, okay, this map here is surjective. O of LD. Okay, so let me make a little remark here. So this is really, so given this identification, that this map is associated to this linear series, so this is really this linear series here. This part is really the degree L part of this, and this is a surjection. So it's saying that this is like a closed, so the graded ring, so the Cox ring associated to this, where you kind of put all these things together and then give this put all the L's together and give this a graded ring structure, that this is going to be a closed subscheme of here. The closed subscheme C0 is when you make a ring by twisting the structure sheaf. But note that twisting doesn't really make sense on C because C is not embedded. Okay. The fourth thing is that phi is an isomorphism. Okay, so this is a birational map. Okay, so this means that the function fields are the same. Okay, but if you have a morphism between two smooth curves, which is birational, then it's automatically going to be then it's automatically an isomorphism. So this is a fact about curves and uses curves strongly. All right. So let me say something about these. Okay. So some remarks on the proofs. Okay. So for 1 and 2, okay. So here we have these two things. So there's already a subspace here, okay, and so we already have subspaces, and so you really want to compare our R of LD and beta of L. So you can see this from the Caswell-Novo inequality, but you kind of get them to be equal by sandwiching. So you get them to be equal. By sandwiching. So you do a kind of sandwich inequality. Okay. So for 4 implies 2. So here, if we have an isomorphism, okay, this is clear because these are going to be exactly equal to these things. So so the pullback of the so what do I want to say? I want to say the pullback of the twist is the twist of the pullback for the structure sheaves. So I claim that this one's clear. Okay. For 3 implies 2, and 2 implies 3. So these are the same thing. So this. Okay. So what does this remark say? Here, okay, if we look here, okay, it's really saying that all the relations on these guys are really coming from hypersurface relations. So this really says that all relations between the various H0C of O of LD are hypersurface relations. Okay. Okay, and this is believable. And then 4 implies 3. Okay. So this is saying that this is an isomorphism. Okay, so then you have the Cox ring here, right? And it's saying that the Cox ring is so there's this Cox ring. So when you put these all together, you get a ring called RD. Maybe sometimes it's called the Iitaka ring. So you get this ring RD, and then it's saying that this is the same as the graded ring for this embedded curve. Okay. So that's what I wanted to say about this. Okay, and then if these are the same, what I said before that about this surjecting onto here, makes this a closed subscheme here. So let's see. So this is an isomorphism. This is okay. If these two things are the same, right? Oh, and this is a closed subscheme, right? Then this is going to surject onto here. Okay, but there's something to be said that these two things are not the same, but this same as means like up to a saturation, I think. All right. So I'm not going to call this a proof. I'm going to say that this is some conversation. I guess the hard part, I claim that the hard part of this is to get 4 from these. So to be deriving 4 from these conditions. And so apparently you want to show that in this that this is going to be, so that you're going to get some non-singular things, so that you're going to get normality. And I'm not sure how to get normality from these things. So, but either way, we're going to have an isomorphism in the Noether setup, so it doesn't matter. And the easier directions are taking an isomorphism and going this way. That being said, let me state another thing that we have. So we need the Clifford Equality. So there's a Clifford Equality theorem. Okay. Suppose. Okay. So remember, Clifford's inequality says that when you're in the range of 2g minus 1 to here, then you're going to have this inequality that r is less than d over 2. So this was this thing about the admissible GRDs. You look at the Riemann-Roch. You had this like Riemann-Roch graph here, and then you had this Clifford line, and you said that admissible GRDs had to fall within this range here. Okay, so this was d and this was r. Okay, and then like here was the canonical divisor. Well, it's supposed to meet this. Okay, so this was the whole thing. You can see the video on Clifford's inequality here. But there's a special situation that we need, and it says suppose equality holds in Clifford's theorem. Holds in the Clifford situation. And Clifford situation. Then one of the following holds. Okay. First is that C is hyperelliptic. And phi d. So d is the degree of d. So this is some divisor, and phi d is a G12. So or this means that that it's this is the hyperelliptic map. Okay, and recall that a GRD is just a so it's like a linear series where you get a projective space of dimension r, and then it's embedded as degree d, or the image curve is degree d. Okay, so two is that that d is a canonical divisor. And phi d is the canonical embedding. Also, I think in the Clifford situation, we have to restrict to genus. I think. Well, I know for sure bigger than 3. I think greater than or equal to 2 is fine. Maybe there is no nothing, so we'll have to see. Well, I'll have to look back at that again. Okay. Either way, this is what we have. We have this piece which says that okay, if you have a Clifford equality, right, that can only happen in hyperelliptic situations or the canonical divisor situation. Okay. So okay. So now let me say the theorem. The theorem of so the Noether's theorem. So this is the Noether of Brill-Noether theory, which is not Noether. Okay? So let C be a smooth curve. And suppose its genus is bigger than or equal to 3. Okay, and suppose that in addition, C is not hyperelliptic. Okay, so we're supposing it's not hyperelliptic, so that the canonical embedding is so the canonical map, so the map associated to the canonical divisor is an embedding. So this makes, by the way, makes phi of C. Or phi of k of C, and an embedding. Okay, and so then for all L bigger than or equal to 1, this implies that this map here from H0 of k of, from the symmetric power here to H0 here. This is surjective. So for all L bigger than or equal to 1. So okay, we have this surjectivity here. And so this is the theorem that I'm going to discuss. And it's really short. Okay, the hard part was that fact that I said. Okay, but since we were given since we're going to be given an isomorphism for the canonical divisor, then the setup's going to be nice. Okay, so proof of Noether, or Noether, right? So we know that so g minus 1 is equal to 2g minus. Okay, so I guess I don't really need to say this, but let me make a little remark, side fact. Aside. Okay, so here this is the degree of the canonical divisor here, and so this is so here this is these are equal to each other. So we're in this extremal situation, right? Or so the Clifford equality. Okay, I guess we don't need Clifford's equality for this. Oh well. Anyway, so let's. Okay, whatever. I actually don't need Clifford's equality. Interesting. Okay, so so we are in the situation of the fact with phi of k of c being an isomorphism. So all of those equivalent conditions hold. Okay, and so this tells us that so there's so by part 3 of the lemma of the fact, we have the embedding. So let me show you again what these facts were. Okay, so here we had these equivalent conditions. So here we had these things that was given in the proof of the Castelnuovo theorem. Okay, the Castelnuovo inequality. And it turns out, so when you have an isomorphism, that this is going to be surjective. So these two things are the same, right? These two guys are the same. So this ring here, so the Cox ring associated to the divisor is going to, the proj of that is going to give you the same embedding here. Okay, and so this guy here is a closed subscheme here, so which means that we're going to have a surjective map from here to here, which means we're going to have a surjective map from here to the Cox ring associated to D. Okay, and that's what gives this. So that's easy. That's easier to see. Okay, that's all I have to say. So thanks for watching. Bye.